Welcome, everyone. Can everyone hear me loud and clear? Yes, great. Also in the back, great. Cool. Okay, my name is Fareed Rashid. I'm the organizer of Building the New Web. Thank you all for coming on this pretty cold Sunday afternoon. I don't know if you guys would mind, but would you mind coming a little bit more to the front? It's more fun for the speakers and better for the camera and stuff like that. I'm trying to get as less empty seats as possible. Okay, so my name is Fareed again. I'm organizing Build a New Web. This is the first edition ever in the United States, and that's because this week is pretty big for the blockchain community here in Denver. There's ETH Denver and Colorado Blockchain Week. Dan, who's on the camera right now, is very much involved with that. So I'm very fortunate to know him. So for today, we have NuCypher and Harmony doing 2 talks of roughly half an hour each. And they'd love to have a lot of questions from your side. This series started basically to get more developers involved with blockchain, but also to get blockchain more to also a more mainstream audience. And we think those things can go together. But I would love to see some hands just to know what kind of crowd we have over here. So I'll just ask some very, very general questions. Who has heard about Bitcoin? Okay. Who has invested in cryptocurrencies? Like half. Okay. Who knows NuCypher and Harmony, both projects? Of course, the people who work there. Great. Mr. in the back. Okay, great. Who's a developer? Like an engineer? Okay, great. Who's a blockchain developer who works in the crypto industry? Okay, like 6, 5, 6. And who wants to work in the crypto industry but isn't involved yet? Okay, great. So, MacLane Wilkison is going to kick it off. He's going to attach his laptop to the screen. Please give him a warm round of applause for coming all the way to Denver to do this. Thank you.
Hey everybody, my name is MacLane Wilkison. I am one of the co-founders of NuCypher. NuCypher is a data privacy layer for blockchain and decentralized applications. So our sort of reason for being as a company is to build the cryptographic primitives and infrastructure that make it easy for all of you all as developers to build privacy-preserving applications. We have really 2 core pieces of technology. One is our Proxy re-encryption network, which will be the sort of focus of my talk today. And then the other is some longer-term research that we're doing around fully homomorphic encryption and lattice cryptography more generally. But the focus of this talk will be on the decentralized proxy re-encryption network, which is a layer 2 access control protocol for DApps. It uses something called threshold proxy re-encryption, which we will explain and walk through. But the obvious question to ask is, what are the limitations of just traditional public key encryption or traditional asymmetric cryptography? Why can't you, as a developer, build a decentralized application that uses these basic, very well understood, very secure, fairly easy to use tools? So take traditional public key cryptography. We have Alice, a data owner or a sender of some message, and Bob, a recipient who she wants to get that message to. With public key or asymmetric crypto, she can just encrypt that message with Bob's public key, send it across the network. Bob can decrypt with his private key. So far, so good, super easy, super straightforward. Where it starts to get a little bit more less secure is, let's take the context of an actual application. So we have some web server somewhere, and we want to use public key cryptography for access control. So Alice will upload some data, say Google, Dropbox, wherever. Originally, it's encrypted under a key, but if she wants to share that data with some recipient, so most applications are multi-user, they require multiple users to access some shared data set, that data will have to get decrypted server-side and then encrypted again for all of those recipients. So fundamentally, we basically have the server as a sort of single point of failure, or honeypot, where all that data is getting decrypted and re-encrypted. So if we're using all these, central service providers like Google, Facebook, Dropbox, maybe we trust them, maybe it's fine, but maybe we don't trust some of the people that are trying to break in to those providers, like state actors or black hat hackers. If we take it a step further to a decentralized application, this idea of server-side decryption is a complete non-starter, because now we're not sending data to a machine that's sitting in Google's data center or Facebook's data center. It could be an IPFS node sitting in some random person's basement or controlled by some malicious nation state. So the idea of having everything decrypted server-side in a blockchain context, particularly if it's sensitive data, makes no sense at all. So we need some way to kind of close this loop and have everything be encrypted end-to-end from the minute it leaves Alice's, the data owner's premise, to when it gets to the ultimate recipient. And we use proxy re-encryption as the way to do that. So what proxy re-encryption allows us to do is is for Alice to encrypt data under her key, send it to some remote storage, and then use some remote untrusted proxy to actually rekey or re-encrypt the data so that it goes from being encrypted under her key into being encrypted under some other recipient's key. And the magic of proxy re-encryption is that this can happen without ever decrypting the data in the middle. So this proxy that's performing this re-encryption never sees the plaintext data, they just see ciphertext. The storage layer that's storing the data also only sees ciphertext. And she can delegate that access to Bob or Charlie or Dave or Evan, as many recipients as she wants. As part of this, we introduce a couple additional characters sort of to this traditional Alice and Bob narrative. One is Ursula, who is the proxy who's performing that re-encryption. And the other is we kind of differentiate between Alice, who might be a policy owner or the ultimate data owner, and Enrico, who is something we call the data source. So in many applications, Alice and Enrico will be one and the same. You're writing a message to your friend and you're encrypting it. In other applications, they might be different. So let's say I'm Alice, I have a bunch of devices, let's say my watch, heart rate monitor, something, that are generating data for me, but they're not me. So we call those data sources Enrico, which is a little bit easier to reason about if we introduce that character. So if we try to build, going back to what we talked about before, if we tried to build some sort of access control network with just public key encryption, we had a bunch of nodes that were receiving encrypted data and then sharing it on with someone else with traditional asymmetric cryptography. Basically, any node in that system would have to access the data, decrypt it with Bob's, the recipient's key. So again, as we talked about before, it's a complete non-starter because any single node has access to the data. Any single node could just refuse to re-encrypt and block access. So one thing we could do, again, is maybe take it a step further. Instead of one private key, we could use something called Shamir secret sharing, which allows us to split that private key up into many different shares. So we could use basically a quorum of nodes all come together in order to grant access or decrypt and re-encrypt again. But the problem with this is that if enough threshold of those nodes collude and work together, they can reassemble a private key, decrypt the data, get the plain text. So now we'd say, okay, what if we just used traditional proxy re-encryption? So instead of sending the private keys out to the nodes, we send only these re-encryption keys that can only be used to re-encrypt data. That's a lot better, but we still have this problem of any single node can just deny access. So if I have my re-encryption key with an Ursula node somewhere, and that node goes down, or for some reason it doesn't like Bob, it refuses to re-encrypt for him, he can get his access denied. We also have this problem of, let's say the sender only wants to grant access to Bob under some certain conditions, like if Bob pays 5 ETH to their address, or after some period of time has elapsed. If the recipient, Bob, colludes with that Ursula node, they can kind of circumvent any of those conditions. So it's better, but we're not quite there yet. And what we've done with NuCypher is, well, okay. So this is kind of what that would look like. So if we just had one Ursula node performing proxy re-encryption, this is Alice. She's got some data she's generating locally. I guess you could consider her laptop to be Enrico, a data source. She encrypts that data, and now she's shipping it off to some remote storage. This could be IPFS or Swarm or Amazon S3. It doesn't matter. You could use any storage layer you like along with NuCypher. And if Bob at this point tries to access that data, he's not going to be able to because it's encrypted under Alice's key, so his private key is totally useless in this scenario. But later on, let's say Alice wants to grant access. to that ciphertext to Bob, what she can do is she can create something called a re-encryption key. And a re-encryption key has two inputs. One is her private key, and the other is Bob's, the recipient's public key. So she'll create that re-encryption key. It's a one-way function. There's no way to get the private key back out. And she will send this re-encryption key to an Ursula node somewhere. And this Ursula node will accept that re-encryption key. And then when Bob requests access to the data, she will use it to basically re-encrypt the data for Bob. And the reason she'll do this in the NuCypher network is the Ursula nodes are basically compensated. So they're paid fees in ETH, and they also participate in block rewards. They get additional NuCypher tokens. So once that payment has been made, Bob will provide that Ursula will provide that re-encrypted ciphertext to Bob. He'll be able to use his own private key to decrypt the data. So that's great, but we still have the scenario where if this Ursula node goes offline, or for some reason it's malicious and it just denies Bob access, there's not really anything we can do about it. But what NuCypher uses is something called threshold proxy re-encryption. So similar to Shamir's secret sharing, which you can use to split up the private key in a bunch of pieces, we can also split up that re-encryption key into a bunch of pieces. So instead of sending a re-encryption key to one node, we'll split it up into, let's say, 5 shares. We'll issue those 5 shares out to 5 different nodes in the NuCypher network, specify some threshold number, let's say 3. And as long as 3 of those Ursula nodes perform their re-encryption and are online and are behaving correctly, Bob will be able to access the data. And so this is pretty straightforward. This is a re-encryption key. We splice it up into a bunch of shares, send each of those shares out to different nodes in the network. And as long as that threshold number, M of n, so in this case 3, are online, everything's good. So the NuCypher network basically consists of a bunch of these Ursula nodes that are accepting these re-encryption key fragments. They're storing them, and then they're enforcing any policies that the data owner might have specified, whether that's payment or time or any arbitrary condition. And the function of the NuCypher token is basically a staking or a bonding token. So if you want to be one of those re-encryption nodes and make money sort of as your business, you have to stake the NuCypher token as a kind of bond or collateral. So a useful analogy might be like a taxi medallion, where if you have a taxi medallion, you have the right to give people rides and make money. If you have the NuCypher token, you have the right to stake that token, provide re-encryption services, and make money. We also use that to coordinate the network. So if you're staking 5% of the tokens, you'll get 5% of the work. If you do that work correctly, you'll get 5% of the compensation. If you do that work incorrectly or become malicious, you go offline. Instead of properly re-encrypting, you just provide gibberish or garbage. You can get your stake slashed, so it's an economic incentive for correct behavior as well. These are a few of the applications that people are building on top of NuCypher. As you can see, quite a bit of healthcare, so projects that are building patient-controlled medical record systems, some IoT where they got a bunch of data, or a bunch of edge devices that are streaming data, and they need some way to secure those. Another very interesting database use case are data marketplaces and data exchanges, like Datum or Ocean Protocol, that are aggregating different kinds of data, and then they're trying to monetize it by auctioning it off or selling it to researchers or advertisers. So this is where you could use a kind of conditional access delegation in exchange for payment. And so now I will do a quick sort of demo of what this looks like from a developer standpoint. So in this case, in this demo, we'll have each of the 4 different characters. So we'll have Alice, who is the data or the policy owner. We will have a heart monitor, which will be a data source or an Enrico. It'll be generating basically heart rate data or monitoring her health. And then it will be encrypting that heart monitor data under Alice's key and storing it in some remote storage, whether this is IPFS or Swarm or S3. It doesn't matter. And then Alice will want to share that heart data with Bob, who is her doctor. And when Bob wants to access the data, he'll fetch it from storage, download it. At this point, it's encrypted under Alice's key. He has no way to access it. He'll send a request, an access request to the NuCypher network, which will do the re-encryption. And after that, he'll be able to decrypt with his own private key. So This is basically the script we have for Alice. So we'll skip some of this setup stuff. But you can note that for Alice to interface with the network, she obviously has to know about the network. So we have some seed node that she'll learn from. In this case, I'm just running a local network on my laptop. So she'll connect to this local host on port 11500. What we'll do is we will basically get our Alice character. So we'll check if there's one saved on disk. If not, we'll spin one up from scratch. And in our code, we actually use these Alice, Bob, Enrico, and Ursula characters. So what will happen is we'll basically tell her the seed node to learn from. We're operating in federated only mode, which basically means we're not using a blockchain. There's no staking in this network right now, just because I'm running it locally. We will initialize that Alice. And then at this step, basically, this is when we'll tell Alice to learn about the network. So we use something called a learning loop, which is basically a way for a new node or someone to bootstrap into the network and learn about all the different nodes. So they'll connect with a seed node, and that seed node will tell them about other nodes they're connected to. And pretty quickly, they'll kind of get a picture of the full network. We use this concept of labels. So this is almost like a file path, a directory, so it specifies some data that we want to grant access to. So Alice might have a bunch of different data sets, art data, social media data, email, photos, whatever. In this case, she doesn't want to grant access to the doctor for all of her data. She just wants to grant access to her health data. So we'll just label that heart data. And then she will create a policy public key. And this is the public key that all of the heart monitor data will get encrypted under. We'll use this heart monitor, generate heart rate samples to just generate a bunch of sort of dummy fake data. We'll just save it locally for now, but in principle, in a real application, we would save this in IPFS or Swarm or somewhere. And so let's say some time passes, that data is just sitting up in Alice's storage. Later on, she decides she needs to share this data with her doctor. She needs the doctor's public keys, so she needs the public key of the person she's granting access to. And then she will create a Bob character, a recipient, from those public keys. We want to specify some conditions for this policy as well. And in general, these can be kind of any arbitrary conditions you can specify in a smart contract. We'll keep it pretty simple here. We'll just have a policy end time. So we don't want to grant Bob access forever. We only want to grant him access for, in this case, a week, 5 days. And then m out of n, this is basically where we set the threshold. So since I'm running this network locally, I only have one Ursula node, so m of n will just be 1 of 1. But if we were using the actual real network, you could set 3 of 5 or 5 of 10 or whatever threshold you like. And then we will have all the data we need for the policy. We will issue it out to the NuCypher network. And at this point, once this function has run, that network has been living out in the NuCypher network. And if Bob were trying to access it, he should be able to decrypt the data. So we can execute that script to get it out there. So you can see in the learning loop, it found the one node that's currently running in the network. We basically have code names for all the different nodes. In this case, it's this medium turquoise, star green. We created the public key for the label, and we created the access policy for Dr. Bob, and we issued it out to the network. Now, Bob wants to actually access that data. So we have a similar script for him. He's going to connect to that same seed node, which is just on localhost. To decrypt the data, obviously he needs his own private keys, so we'll initialize all of that. We'll create this doctor character who is Bob class. And then we want to actually join the policy that Alice created for him. So in this case, we just stored it locally. We'll grab that out. we'll grab the label for that policy, which is heart monitor data. We'll join that policy. We'll verify it using Alice's signing key, and then we will download the bulk data from storage. And at this point, it's all encrypted under Alice's key. Dr. Bob has no way to actually access it, so he needs to send a request out to the NuCypher network to perform this re-encryption. So for each piece of data in that data set, he basically will issue a different request to the NuCypher network, get those pieces of data re-encrypted, return to him. At that point, he'll be able to use his own private key to decrypt the data. We'll just use the formatting here, and then we'll just print out that plain text data. And if it works, we should see a nicely formatted sort of stream of heart rate monitor data. So you can see he connected to that same Ursula node, seed node. He joined the policy, and then he started getting these heart monitor streams re-encrypted for him and printing them out. And in principle, we could have many other Bobs. So maybe she wants to share her heart monitor data with her insurance company to get lower premiums, or her family or something like that. She can create policies for as many recipients as she likes. She can also revoke policies. So let's say she switches healthcare providers. She no longer wants to grant access to this doctor, but a new one. She can revoke his access, issue a new policy for the new doctor. So right now, we are running about a 50-node private testnet with a bunch of our early staking partners. We did our Genesis or alpha release last month, which included a lot of documentation. So I'd encourage you to check that out if you're interested in potentially building something with NuCypher. Over the next several weeks to a month or so, we're hoping to have a public testnet where anyone can grab testnet tokens from a faucet, stake those, and run an Ursula node. And then hopefully sometime late spring or early summer, we're hoping to launch mainnet once we make sure that public testnet is working and stable. And I'll also at the very end just touch on some of the research work we're doing around fully homomorphic encryption. For those of you who don't know, homomorphic encryption is this idea that you can do arbitrary computation on encrypted data. So in the same way that you can do a computation or process any arbitrary plaintext data, homomorphic encryption is this idea that you can do those same functions or same processing on encrypted data and get an encrypted result. So we think this has a lot of interesting applications for a lot of stuff in the blockchain space, so private smart contracts, potentially privacy-preserving payments, things like that. We have released some of the work we've done, which is this new FHE library, which is basically a GPU acceleration of one of the existing schemes called TFHE. And we were able to get about 100x performance over vanilla TFHE benchmarks using GPUs. Right now, we're about 7,000 gate operations per second. And Tux, who is somewhere or back there, actually used this library at ETH Berlin, at this point, I guess, 4 or 5 months ago, to execute the first ever fully homomorphic smart contract. This is all open source. I'd encourage you to check it out. Right now, it's more of a proof of concept library, so we don't recommend to use it for anything in production. But we're putting an increasing amount of resources towards FHE, and I think it's actually a lot closer to reality than most people generally think. So that's it from me. If you'd like to learn more, definitely please go to our website. Again, we just push out a bunch of documentation. That's docs.NuCypher. All of our code is open source. You can see the proxy re-encryption network on GitHub. Our threshold proxy re-encryption scheme called Umbrel. Also the new FHE library. And then all of our engineering and development discussions happen in public on our Discord. So we'd be happy to see you guys there or help you if you're building any kind of application or just have any general sort of technical or development questions as it relates to NuCypher. Thank you very much.
Yes. Thank you, MacLane. Exciting demo. Questions? I'm running.
Hi, my name's Dan. Just a really simple question. how do you intend when you go into production to stake the the nodes, the Ursula nodes, and what does that look like? Is it really simple? Is it really a process that you guys are going to sort of keep behind the curtain? I'd love to hear what that looks like.
So we definitely won't be keeping it behind the curtain. I mean, the function of the token is for staking, so we want as many node operators as possible to be staking and working for the network. So that'll all be documented. When we have mainnet, we'll have some sort of token distribution, so that's when the token will go live. We don't know the exact sort of nature of what that will be, whether it'll be some sort of airdrop or some other issuance mechanism. But yeah, that'll all be documented. Basically, it's an ERC20 token, so you'll stake that token into a smart contract. That will give you the ability to then run a node for the network and receive work orders and compensation. So we're trying to make it as simple as possible. We have some of the code in the code base right now for staking. We haven't fully turned it on yet, but we're definitely open and interested in getting feedback on the API for that and sort of the experience as a node operator.
This is sort of a more practical infrastructure question. As you know, a lot of the internet is sort of still the Wild West as far as cyber is concerned. Just speak for a moment about what happens when one of your nodes is really being affected by the internet weather in the area. How do you guys see sort of a graceful degradation, if there is one, based on practical infrastructure considerations?
Yeah, so that's a really good question, particularly when you consider that we have the slashing protocol. So if a node misbehaves, it's at risk of potentially getting slashed. And there's really, I would say, two modes of misbehavior. One is a node that's actively malicious, where instead of properly re-encrypting, it's just returning garbage data or gibberish or nonsense. And that's actually very straightforward to detect. So you can generate cryptographic proofs of re-encryption. And so if we detect that a node is maliciously re-encrypting, we would slash that node fairly aggressively. The exact parameters we're still working through, like will they get their entire stake slashed or some proportion of it? But in that case, the node will definitely get slashed. The other mode of misbehavior is if a node just goes offline. And actually, we thought a lot about this, whether we want to slash in that scenario, because it's basically not possible for the network to know if a node has gone offline just because it wants to actively hurt the network, it's lazy, or potentially if it's getting DDoSed or something like that, or the power went out and there's nothing we can do about that. So we've had some discussions on whether we would want to slash in that scenario for a non-responsive node, and we haven't made any sort of final decisions on that. I think what's likely to happen is we would probably not slash in that scenario, but the node would basically just stop getting compensation. So when you stake the token, you also lock the token for some period of time, and you run the node for that period of time, and then after that time elapses, the token gets unlocked. So basically what would happen is you wouldn't get paid for the time you're offline. The countdown to unlocking your stake tokens would also probably stop.
So let's say a party is sending encrypted data with like 3 out of 5 encryption keys. So what would be the incentive for like 3 of 5 not to collude, to decrypt the data? Is it only monetary incentive with a proof of stake, or is there something more? Because if there is some very valuable data encrypted, and maybe 3 nodes have stake, each of them, let's give a number, $5,000, and the value of the data is order of magnitude more than that. How do you prevent such like collusion to happen?
Yeah, so that's a good question. I think right now we're thinking about if there's a way to sort of anonymize the network, so make sort of obfuscate where these different re-encryption keys fragments are going, so that it's very difficult for an Ursula node and to identify who has the other fragments. So part of this is just comes down to how many nodes are out there in the network. I would also note that only the Ursula nodes can't collude. So if 3 of those Ursula nodes colluded, they have no way to actually get the plaintext data. They would have to also collude with Bob, which they may do in certain scenarios. But the only thing they can do if they collude is re-encrypt. So they can't decrypt. So they can just re-encrypt for Bob. So maybe they would collude with each other and a Bob to kind of circumvent some condition that Alice had put on the data. So it's better than just like general like Shamir secret sharing, for example. So there is some sort of inbuilt protection there. You'd have to collude with Bob, who you granted access to the data anyway. So when Alice creates the re-encryption key, a re-encryption key targets some public key. So she'll create a re-encryption key that targets whatever Bob's public key is. And that re-encryption key can only re-encrypt data for that Bob. So it's still a valid question. Like, it's possible that the Ursulas would collude with each other and with Bob. But yeah, we're looking at things like anonymizing the network and other potential mitigations. But yeah, that's a consideration. Yeah, I don't think it's like, I mean, it's something we'd obviously like to fix to the extent that we can. But yeah, it's not like, oh wow, the data's in plain text and totally compromised.
Great talk. Appreciate it. Forgive my ignorance if I'm missing some stuff here, but whenever I'm looking at this, you were talking about sending medical data to Bob. So what I'm understanding about this is that it's effectively a sublet of your prime key. Is that a fair statement?
So in practice, the way that it works is that the bulk data, say the medical records, would again get encrypted with a symmetric key, and then you would encrypt the symmetric key with asymmetric cryptography, and then you actually just do the re-encryption on that encrypted symmetric key.
But if Bob Bob's going to have the information in plain text, yes?
Yeah.
Okay. So if Bob is compromised, then pretty much anything that's done back to that, this is the way that I'm hearing it. And if I'm missing something, by all means, correct me. But what I'm hearing is this is effectively what the NSA is asking for a backdoor into encryption. That's what it's sounding like to me.
I mean, I wouldn't call it a backdoor in the sense that, like, because this is just all standardized encryption. Like, there's no weakening the encryption. If you decided as a data owner you wanted to create a re-encryption key for the NSA and share all your data with them,
right? But they could also demand that if you're going, because this is also somewhat similar to a Tor network, is what it's really starting to sound like also. So if somebody in that Tor network is able to become Bob Plus in any way, then they're going to be doing the same type of attacks that you see on Tor, to have a man in the middle for the NSA to have an encryption to be able to, and I can even see them doing this at an AT&T level, where they're saying we're going to mandate that you have to have that to run. I mean, it seems like it's really...
Yeah, I mean, so the only way that you could get the plain text data is if you compromise either Alice's private key or Bob's private key.
Right, but I'm saying if they mandate a Bob, or if they, in any way, if Bob is compromised, can you...
Yeah, so once you... Yeah, like, I guess in this scenario, like, once you share the data, and Bob has the data in plain text, he can cache it locally, again. That's... We can't do anything about that.
Right.
Like, once Bob has the data in plain text, Bob has the data.
Right.
I don't know of any real solutions for that.
But there's
in general.
Well, one of the things that you have that's going on in here, where you're saying it's only good for 5 days.
Yeah. So when I was talking about revocation, I'm referring. Where is that slide? I'm referring specifically just to the data that's in storage. So if Bob has already fetched that data,
it's in plain text
and has it, and we can't revoke that. But if he has not, we can revoke his access from storage. But we can't revoke access, obviously, once Bob has the plain text or the private key.
One of the things that you may want to look at is having it so that Alice has control of what the information is never truly in plain text, and actually make a reader so that you can revoke Bob being able to read it in any way, which would negate the ability for the NSA questions and those. I mean, you see where I'm going with that?
When you say a reader, you mean like some sort of client-side application that he's...
Yeah, and I know the whole issue with client-side. I'm not trying to proffer that as the answer. I'm just saying some way where you can effectively it's kind of like, I forget the app, but it can set a deadline on a text so that it's only available for so much time. But anyways, it seems like what you're doing.
Yeah, I mean, you can do like certain sort of tricks, but they're not really, I would say, cryptographically enforced, because that disappearing message. If I take a screenshot of my phone, I have it. Yeah, and I would say, like, for certain use cases, like the FHE stuff might address some of that, because let's say, I don't know, you build a 23andMe where all the data is encrypted before it gets to 23andMe. They're able to process that data, generate insights from that data without ever actually seeing the plain text genomics data.